Hello, in our previous video we rigged a classic sport car using standard rigid body constraints, wheel joints, differential axle, and double hinges. When we tested the vehicle in the application, we discovered that it only behaved correctly at very low speed. As soon as the car reaches any reasonable velocity, it exhibits severe understeering, making it difficult and eventually impossible to control. The simulation itself is not incorrect. It is simply behaving the way an assembly of rigid body would under classical Coulomb friction model. There are several ways to make the simulation behave more like a real motor vehicle. A common approach is to make the car front-wheel drive or all-wheel drive. Other techniques involve using the classical bicycle model to calculate the vehicle size, slip angle, and yaw rate, then apply auxiliary torque to limit excessive sliding. To address these issues, the Newton engine provides a set of specialized subclasses that implement the nonlinear dynamic of motor vehicles. These include multibody vehicle, multibody vehicle differential, multibody vehicle tire, multibody motor, and multibody gearbox. We begin by reopening the rig model in the Asset tool. First, we replace the existing wheel object with their corresponding multi-body vehicle component. We select each one and replace its current joint with a multi-body vehicle tire joint. We adjust each tire parameter as needed. It is common to overlook a setting or make a configuration mistake. So after all of the wheels are replaced, we perform a quick inspection of the model and correct any issue we find. The next step is to replace the double hinge joint currently used to implement a motor and differential with a multi-body vehicle differential. We move the node toward the rear of the vehicle to better approximate the location of that component. We also resize the shape. We then rotate the node so that its rotation axis runs across the chassis and the up axis remains perpendicular to the vehicle body. For clarity, we rename the node differential. Next, we need to add an engine node. To do this, we clone the differential node and rename it engine. The node could remain at the same location, but for this demonstration, we will move it closer to the center of the chassis. Now we need to link the engine and the differential through the drivetrain. The joint for this is the multi-body vehicle gearbox class, which implements several drivetrain components of a vehicle, including gearbox, crown gear, clutch, and the transmission logic of a motor vehicle. At this point, the model is essentially complete. However, before saving it, it's a good idea to perform one final inspection. During the inspection, we noticed that the differential node is still configured as a double hinge. So we changed that to a multibody vehicle differential. We also noticed that the engine node is still configured as a double hinge. We must replace it with a multibody vehicle motor. We save a copy of the model and we move to the application for testing. In the application, we first perform a quick crash test by wiggling the motor and observing that all joints are properly set and calibrated. We are now ready to drive the car. We should expect a more realistic simulation that better approximates the behavior of a high-performance rear-wheel drive sport car. The vehicle should remain controllable at both low and high speeds. It should naturally oversteer and drift when pushed to its limits while remaining malleable and responsive. You can further refine the handling characteristic by comparing it and tuning to different parameters in the asset tool. In the next video, we will demonstrate how to model a complex chassis collision shape using Blender. Until then, thanks for watching.